we all talk about the uniform distribution of the mass, right? But sometimes,
Yeah, I didn't really do anything with that because I was doing SAT prep.
like you're gonna take
So I
SAT?
guess we could just continue where we left off.
Yeah. And
What
here
page
is
is that again?
217, I think. Yeah, 217. Because we all talk about uniform, basically the rho is the same. The density distribution is the same. It's a uniform. But sometimes, for example, it could be any objects or anything from the nature. So, I mean, all different parts probably have all different densities. Does that make sense?
Yeah.
So in order to talk about that, we use this one as an example. So this is delta m. Each delta m is a little bit different because the different density. And each one is the delta x. The length is delta x. This is something we use for calculus, like a calculus too. And then we can talk about, here we say the density is a function of delta x. As a different location, for example, this part, they have a little rho like a lambda 1. Let's talk about lambda. They use lambda, we use lambda 2. So, and this part could be lambda 2. And there's a pattern. So the pattern is called lambda x. It's a function according to different x. Does that make sense?
So x for every x, what?
Yeah, for example, it could be like a 10x plus 4. For different locations, different parts, they have different density. Does that make sense?
Yeah.
So of course, then different one have a different delta x, right?
Yeah.
For different delta
wait,
x,
give me
they
a
have.
second, because your 217 isn't the same as mine. I don't know why. Let me see. Is it okay? It is chapter. Okay, I see it now.
So for each little delta x, we're gonna have a corresponding to a delta m, right? It's basically what the rho here. It's a little delta x correspond to each little delta m. And remember when we have well, let's use that. So now we can see I have a lot of delta m times a lot of delta x, and they sigma find out the sum. This is something that we find it before, right?
Yeah.
This should be divided by the big M, which is gonna be getting my x center, right? Center of the mass. This is what we learned before, right? Now it's just to have different density, but still it's kind of like that too anyway. But this one isn't that integration, right?
Yeah.
So
So basically finding all like
delta x,
like the average density kind of.
Yes. Delta x approximately 0, so I can just assume all this is sigma becoming dx and dm, right? Because they're so teeny difference. And I add all of them, that become integration, right? This has become integration. Oh, I have to erase that actually. This become an integration, then it just integration x dm over m. So remember, x is a function of density of, well, function of its density is a function of x. Does that make sense?
Can you go over the integration part?
Well, basically, integration part is that sigma delta m times delta x equals to, because delta x approximate 0, so it's integrate x dm.
Mm-hmm.
Does that make sense? This is integration.
Yeah, a bit more.
Yeah. And then, so basically, this one works. Again, before we just talked sigma mx. And now we talk about integration x dm over m. Before it's like this. If it's a uniform, we use like this. If it's not a uniform density, we use something like this. Does that make sense?
Yes.
And if we go on about this, you can see that lambda is that function lambda equals to dm over dx. Does that make any sense to you?
Oh, when's the last time lambda showed up?
M is just the delta m, each part. So this is the one, so this is each little delta m, and this is each little delta x.
And what's the relationship between them?
Well, I can just time delta x. Because I have delta x, I can find the mass in here, right? For example, if it's a 0.01, I can use that one to find that delta m. But since delta x is so little, it's so small, so delta x approximately 0. Does that make sense? And we also assume that linear density lambda is a function of x.
Yeah, that makes sense.
Yeah, so that linear density is dm over dx. It's for which little teeny tiny part and what's the mass, basically. Right? So little teeny tiny part and what's the mass, basically. So this is this basically is the rate of the change. Does that make sense? That's why it's
Okay. Yeah.
derivative.
Rate
That's
of
why.
the change of the mass, right?
Yeah, before it was dy over dx, now it's just dm over dx. For each teeny tiny part, how fast you increase your density, basically. Does that make sense?
Mm-hmm.
And if this is working by definition, rate of the change, and then on the other hand, the other way is also working by integration, right? I accumulate all the dm, I have my mass, right? Or I accumulate all my lambda times dx, which is dm, right?
Yeah. So you just get mass. Mm-hmm.
Yeah.
Makes sense.
So this is something we also have to remember. This one not used a lot, but this is the foundation, I guess. So we understand now we have two formula. One is so similar as before, uniform density, and the other two is easy to deduce anyway. Because if I accumulate all the dm, of course I get m, right? If I accumulate all lambda times dx, which is this lambda times dx, it's dm, right? Because the lambda times delta x is delta m, right? So that's why lambda times dx must be dm, right? Does that make any sense?
Yeah.
No. We've seen this in like calculus integration. So now because we have this one and this one, we can do example 12. Let's see example 12. I want to explain linear density a little bit. Linear density is because of the length, there is a pattern between the length and the density. Some people ask, what if there is no pattern? Well, then we actually use something similar to deduce the complicated one, but we're now dealing with the easy one. Does that make sense? This linear density is because there is a pattern between the density and that x.
Oh, so now we're looking at it's like facilitated, right? So as x changes, the density changes. Okay.
Yeah.
X meaning like, for example, this here or here, right? Okay. I guess we could just start on sample 2 and I could get a hang of it, I guess.
Yeah, let's do 12.
So a bar with length 30 has a linear density of that, where x is in meters and that is in kg/m. Determine the mass of the bar and the center of mass of the bar. So, okay, you have this equation here, and then this. Okay, that's actually not that bad.
Yeah.
So let's cover some of this. Okay, that's good enough. So center of the mass equals 1 over all the mass, which is wait, all the mass, so it would be
Oh, we can find all the mass because it's not there clearly. With this one, right? You can use this one.
oh yeah. So we use this one first. Yeah, I was drawing an integration sign. And then 0 to 30 of the mass.
Yeah.
So 10x plus 3x squared 30 0 plus 3 times 900. So 3,000. That's that's big M. That's also one of the answers it's asking for. So
yeah,
there you go. And then change of just X dm. So we just do this 0 to 30. Is it like that?
Yeah.
Okay. So times 900 over 2. So you can get 9 over 30, 10 over 3, 3 over 20. And they say 0.154. Let me just make sure that's the same thing.
Yeah.
Yeah, it seems like it.
Yeah.
Yep. Close enough.
Yeah. So then we finish all. It just in the end, it just you can say it's 3 equations. Also, some of the vector of the momentum is not that easy. Like, careful, because in different directions, conservation of momentum all works. That's something to be careful.
Oh, rotation. Woohoo.
Yeah. If we rotate, this is also kind of like trigonometry though, and they are definitely connected. Have you seen this angular velocity?
I remember it looked like a funny shape, but that's basically it. It's like something like that, like a rose. I don't know. But that's basically all I know.
Yeah.
Maybe not. Maybe I'm wrong. I don't know.
So anyway, if I start from here, if I move a delta theta, and my delta theta divided by the time that I do this rotation, that is my angular velocity, right? A little bit similar like a linear velocity, the distance. Now the distance or displacement is just delta theta, right? For angles, right?
So just as the time rate of change of displacement gives velocity, the time rate of change of angular displacement gives. Oh, okay, yeah.
Delta
that makes
x
sense.
over delta t, that's before, right? Now it's omega equals to delta theta over delta t. Delta t is the same, pretty much.
So how fast is the angle changing? Yeah.
Yeah. And because of this, rate of the change. I can also talk about the instantaneous rate of the change of angular velocity, which is d theta over dt. That's making sense too, right?
Yeah, at this moment,
Yeah.
that's how fast it's changing. Yeah, just like how the derivative of like
Yeah.
velocity is just how much it's changed over how much. Yeah.
Yeah. If we use linear, then we have velocity, then we have acceleration, right? Before we have delta v over delta t equals to a, right? This is something we use for linear, right? But now for rotation, in the
Wait,
same
a for acceleration, right?
yeah, yeah. And
Okay.
in rotation, I might want to use the same thing. It just last time it's delta v, now it's delta omega, right? Omega final minus omega initial, right? Does that make sense?
Yeah.
Divided by the time.
What is the acceleration of?
Yeah, angular acceleration. Let's give it a is probably not that good idea because it confuses us with this one. So we use alpha equals to, and also connect it with angles. So alpha, which is angular acceleration, equals to delta omega equals to delta t. Does that make sense?
Yeah, just basic derivative stuff.
Yeah, and then I can also assume instantaneous angular acceleration is delta w, delta omega over delta t, right? This is average, of course. And this is instantaneous. Same thing as this too, right? And also because there is, if I turn like this from here to here, I might also involve with my arc length. My arc length saying is delta x or what, delta s maybe? Yeah. This length is delta s must equals to r theta according to geometry, right? R, let's use delta theta anyway, right? Because this is something that we use. Does that make sense?
R being radius?
Yeah.
Or...
So this is rotation. We have definitely have like a radius, right? Does it make sense? This is arc length, right? Arc length.
So arc length equals the amount of degree you've changed times the radius.
Yeah.
I guess that makes sense.
In geometry, we have r theta equals to arc length, right? Do you remember that? In like a geometry, arc length equals to r theta?
Vaguely. It's been a bit since I took geometry. And I didn't really have to use it for anything. So
yeah, I can prove it. So for example, if I have a little change of theta in here, it's a rotation, and let's think about math. So I can say theta over 2 pi, which is my fraction, right? Times 2 pi r, see? And 2 pi are simplified, is r theta, right? That's the arc length. Does that make sense? I'm using the fractional part.
Oh yeah, because it should be equal to the circumference, right?
Yeah. So the entire circumference 2 pi r times my fraction from the 2 pi, right? This is your theta. This is of course in radian. So theta over 2 pi, or theta if it's in degree, theta over 360 degree, right? I can use the fraction to help, right? So now I proved arc length is the r theta. So this is arc length. I mean, this is arc length. This is r theta, right? Or I'm just talking about delta theta here. So if that's the case, I can introduce another formula, which is, well, I can divide it by delta t, and this is also delta t. So this is a velocity, right? And this is r omega. So now v equals to omega t. Have you seen this before? V
velocity ut isn't. Wait, what does that mean again? Is that the coefficient?
Yeah. It's the linear. Oh, it's the angular velocity. Because delta theta over delta t is angular velocity here, right? See?
Yeah.
Yeah. So that's why I deduce another one. V equals to omega t. I mean omega r. Sorry. Omega r.
This is omega.
Yeah, W is called omega there.
Oh, this is W. Okay.
Yeah, yeah.
W being the no, W is,
Velocity, angular velocity.
yeah. Well, in this case, instantaneous, right? Because it doesn't have a line over it.
Yeah.
So you're saying the velocity of the arc?
Yeah.
What is, okay, the velocity
Velocity
of
of
the
the
arc.
linear rotation. It's basically you're doing this kind of, for example, in here your linear velocity is this one, right? It's the tangential line in here. Does that make sense?
Yeah, so basically the velocity at any given point on the circle is equal to the velocity at which the angle is changing times the radius. Okay, yeah, that does make sense.
Yeah. It's because of this geometry thing. Dot s equals to r dot theta divided by dot t on both sides. So now I can just introduce to this one. Oh, just hold on 1 second. I have my baby scream. Just 1 second.
It's all right, but it's all good. Using the equations V.
Okay.
Rate a change of the, yeah, okay, got it.
Isn't it making sense? This is
Yeah, it does.
kind of going to use it in the future. And also because of that, I can still, well, we have second derivative, but I can still, well, make the derivative on both sides, right? dv over dt equals to, if r is not changed, and it's dw or d omega over dt, right?
D dt. Well, yeah, I get this equation right here, and then if you just take the derivative of everything.
Yeah.
Yeah, and then r stays constant, all that. The derivative of the rate of change. So isn't that just what the thing is right now?
Acceleration.
Oh, wait,
linear.
this is acceleration, right?
Yeah, this is acceleration.
Wait, could you
right?
scroll up a bit? Sorry.
This is acceleration, right?
Yeah.
On the left part is acceleration.
No,
right?
like this. Yeah, I get that, but I'm just kind of confused about this.
About omega? Omega is equals to dot theta over dot t.
Oh, so
Or-
just
Yeah,
that's
or
the
dt.
velocity.
Yeah.
So if you were to take the derivative, that would also be acceleration.
Yeah.
No. Yeah.
That was also angular acceleration.
Mm-hmm. Yeah, because taking the derivative also always makes you like get acceleration from velocity. Yeah.
So with this in our hand, I think we can do some of the questions here. Let's do example one.
This one's actually kind of nice and new. Okay, a rotating rigid body. Let me just clear all this.
Yep.
makes one complete revolution in 2 seconds. What is its average angular velocity? So in 2 sec, that means v equals to pi r every second. Let's say meters per second. I'll just keep meters for now. I'll get rid of it later.
Okay.
So that's what it is. And then what is
Wait.
its angular? So
You're thinking about linear, right? But they are talking about angular.
oh no, I'm finding its v first. So then I can do what is it? Pi r.
Yeah, it's also okay, I guess.
Equals w or omega times r. So these r's go away.
That's the last formula. But the before is actually omega equals to theta 0 over theta t. I think that's probably easier. But in your case, in your situation, it's also working, I guess.
Okay, yeah, I guess it'd be nice to try a different one as well.
Sure,
Okay,
yeah, you can use
let me just clear that. So equals change in. Okay, so change in time is 2, of course, and then change in theta would be 2 pi.
Yeah.
So it's just pi.
Yeah.
Okay.
Yeah. In your original method, you can find v and divide it by r, which is also the same. And that v is actually called 2 pi r, right? And divided by, well, do we know r? Oh, we don't really need it. 2 pi r over t. And then it's 2 pi r over t over r, right? It's still 2 pi over t. Same thing anyway, right? So this is example 1 and 2.
A rotating rigid body.
Wait.
Yeah.
Here, example 2.
Oh, whoops. Angular moment velocity of a rotating disk increases from that to that. What is the disk's average angular acceleration? Okay. I feel like I could do this. So we need to find its acceleration, right? And then we can do its acceleration equals r times, and then yeah, r stays constant, and then no, not this is not angular acceleration. This is that how much this velocity changes, this thing equals angular.
Oh, you mean it's v equals to r omega? Or
oh wait, no.
a equals to, we have several actually. A equals to r, wait, let me think. R alpha. Or we have alpha equals to delta omega over delta t. They all have alpha. No, these two have alpha.
Okay.
So alpha is the angular acceleration, right? This letter is confusing.
Oh yeah, because it's radians, right?
Yeah.
So
this is just a kind of certain velocity, you have to say. Oh, angular velocity.
okay, yeah, and then its velocity equals to change in, was it, no, your
If it is more directly, I'd probably use this one.
this meaning the acceleration to
angular
okay, yeah.
Angular acceleration. You can just omega like a final minus omega initial. You should give it already. 5 and 2.
Change, wait, okay. W meaning
Angular
it's
velocity.
yeah. So change in angular velocity is 3.
Yeah.
And then time is just 0.5. Okay, yeah, that's starting to make sense. Just more equations.
Yeah.
Okay.
Which
Yeah,
is
6.
6, right? 6 reading per second
Great.
square, right?
Mm-hmm. Yeah. Okay.
Yeah.
Maybe we should do a few more.
Yeah. And 3.
A disk. Okay. Radius 20 centimeters. Rotates at a constant angular velocity of this. Velocity. It's constant, so no acceleration. How fast does a point? Okay, yeah, that's manageable. So the rim velocity, this thing. I don't. What's the symbol for this again?
Wait, this? What is this?
Yeah, like the velocity at any given point of the circle.
If it's talk about linear, it's v.
Oh yeah, V.
The other
Okay.
one is omega, angular. That
Mhm.
corresponds.
Yeah, I knew that one.
Yeah.
Just so V equals to 20, of course, times how fast it's changing. So 6 radians per second. So isn't that just 120?
Let me think. It's a zero. It's 20 centimeter. So which means
Oh,
we probably
meters.
use
Okay.
meter, right? 0.2.
Whoops, I did not
right?
see that.
No. Oh, you're using v equals to r omega. Oh yeah, sure.
So just 1.2 meters
Yeah.
per second.
Yeah. Well, finally we're using this one. Good. I like that one. A little more complicated. We're using something before. 4.
Mhm. The angular velocity of a rotating disk of radius 50 increases from 2 radians to 5 radians a second. 0.5. So it has acceleration. What is the linear tangent? Okay. So the derivative of v dx equals what? Okay, so that equals the change in velocity over the change in time.
Yeah.
Oh no, w, right? Wait. This is w. What? No. Wait. Change in velocity over change in time equals. What's the
This is
equation
something.
again?
This is something which is just from the previous question, right? They're the same background, right? 2, 5, and 0. I mean the example 2. Let me see example 2 for a second. Oh yeah, same thing. 2 to 5 in 0.5 seconds. We find angular acceleration at that one, right? For example 2. That's the same question. Example 4 is just the follow-up.
Okay, so
which means we have alpha.
Okay, so yeah, like angular.
It's a 6, right?
And then you take that and then you make it 6 times the radius.
Yeah,
exactly. This. Wait, let me check if it's in the right units. Yeah, so Is that right? The units?
3. Let me think. It's
Or is
a
it centimeters?
0.5 meter probably, because it's 50 centimeter. This one.
50 centimeter.
Yeah. We talk about a meter probably.
Oh,
0.5.
okay. So
3 then.
mhm.
6 times 0.5. It's 3, right?
Oh.
Mm.
Okay,
3
yeah,
meters.
because 1, 2.
Mm.
Oops.
And 3 meters for 1 second. It's not very fast, right? You're talking about the turning of the speed.
Okay, yeah.
And turning in with the CD is also not very slow, right? You've seen this thing circling, right? Not very slow.
Yeah. Mm-hmm.
Let's talk about 5 then.
Terms of angular speed. Centripetal acceleration. So basically this thing that pulls it in the center.
Yeah.
In terms of angular speed. I guess you could say that the acceleration of the tangent line.
Mm.
But the acceleration of the tangent line is this way. So I'm kind of
Yeah,
confused.
Yeah, so because the centripetal acceleration for us is always A equals to V. We can forget about what we learned today for a second. It's always A equals to V squared over R, right? That's what we always use, right?
Yeah, for the centripetal.
Yeah.
Mhm.
But now it seems like they don't want to use angular velocity V anymore. They want to use angular. I mean, they don't want to use the linear velocity anymore. They want to use the angular velocity, angular speed now.
Oh, so you could just take that V, right? Because
Yeah, V
it is
omega.
V equals I times the velocity of the thing.
Yeah.
So just plug that in.
Yeah, I can just substitute.
It's a time. It's a dot right there.
Yeah,
R.
divided by R, and then it's omega square R. Yeah.
Okay, yeah, that makes sense.
Eventually, this is also useful a lot of times. So now for acceleration. So, well, centripetal acceleration, this one is also used in quite a lot of places.
Wait, isn't it supposed to be R squared?
R and R simplified.
Oh,
this R and this R.
okay. I don't know what I was doing wrong.
Well,
Okay,
you can
okay.
if you leave it there, still right. So this is the acceleration that we can find for centripetal, for circular motion, basically. Now, when we discuss like rotational, we use linear a lot, right? We use linear, basically use velocity stuff a lot, right? Formula a lot. Basically, everything I use is from there. And so now let's talk about the big 5, which is big thing in those linear motions, right?
With that constant acceleration.
Yeah. So all the big 5 probably correspond to all kind of big 5 for rotational, right? Does that make any sense?
Yeah.
Yeah. For example, what's our big 5 before?
Maybe this one. 0 plus.
VT?
Was it V?
Yeah. VT. V0T. Yeah. Or VT. Oh yeah, sure.
And then that will turn into.
This is delta x, so we can just say delta theta, right?
Change in theta.
Yeah. Delta theta equals to your V0 is becoming my omega 0, right? Means initial
Why
angular.
is it delta theta instead of like delta?
Or otherwise, I have to write theta equals to theta 0. That's just a little too much. You can write theta equals to theta 0. Does that make sense?
Theta 0?
Or if you want to use this way, it's theta equals to theta 0, right? plus
Oh, so basically change in theta. But why would it be that instead of like
x.
movement around this?
Because I want to basically move all the formula that I learned from translational motion, from linear motion, and all into angular motion. Does that make sense? Of course, I can check out all the data whether it's still working or not. Does that make sense? And also, I talk about this one is the big five required is the uniform acceleration. This one required is the uniform angular acceleration. So I can use this one plus t plus 1/2 a, and now angular acceleration is alpha, right? T is the same. Is this okay? This coming from here. Does that make sense? Because well, I wrote this one as delta x, so this one is delta theta. It's probably making sense more. Of course, delta x is just what you wrote as x minus x0, right? That's delta x, right? Does that make sense?
Yeah.
And for the big five, before we also have v equals to v0 plus at, right? So this one I have omega equals to omega 0 plus alpha t, right? Because this one is acceleration, this angular acceleration now, right? Does it make sense? Coming from there. I mean, without proving, I don't want to prove out of the way, but I have to check with all the data. It actually checks.
Yeah.
Yeah, and then we have what else we have?
So it's like the big five, but for okay. Should I remember this? Like.
Yeah, no, you don't have to. You can just always, for me, it's just always write the original big five and make it all into the angular one, and that'll be okay. And after several exercises, you probably get a feeling about it. And of course, we are trying to skip away. We're trying to skip quite a few about proving about angular, but we kind of prove it in translational. We kind of prove it in the linear, so we don't want to do it anymore. We just want to check. So this is another formula. And before, we also have delta x equals to v1 over v2 divided by 2 times t, right? And now I can just say delta theta equals to my omega 1 plus omega 2 over 2, which means average angular velocity times t, right? This is also working. And then what else do I have? I also have v squared over v0 equals v0 squared plus 2a delta x, right? So now I can just say omega squared equals to omega 0 squared plus 2 alpha correspond to a, and delta x correspond to delta theta. So that's another one, right? Two. And the last one is someone that I don't really use a lot, which is if I know the final velocity, which is delta x equals to vt, final velocity minus 1/2 at squared, right? So for this one, I can use delta theta equals to omega t minus 1/2 alpha t squared. Is that okay? You don't have to memorize all this. Just there's a table, you can just always go for it. See, there's a table.
Oh, provided by the thing.
Provided by the sheet. Yeah, it's provided.
Okay.
And also, if you get confused, you can always, of course, you should memorize it maybe after the exercise. Let's use all this. You remember, when I get confused, I just always return to the big five I already know. And then just correspond to each one of them.
Okay.
6. Let's do 6 with all these formulas.
Let me go to that page real quick. Okay, so an object with initial angular velocity of 1 radian per second rotates with a constant acceleration. 3 seconds later, the angular velocity is this. calculate the displacement. So what is missing? No, it's not acceleration.
Mm.
Wait, it might be acceleration because it says it's constant. So oh, it doesn't give you the no. It's asking for it. So asked angular displacement is in there. What is A again? A is acceleration. No. What is A again?
Oh, A is just the acceleration, linear acceleration.
Oh.
Alpha is when they say this one is not A, this is alpha. Otherwise, it confuses us with this one. This is linear acceleration. This is angular acceleration, alpha. Looks like
Okay.
A though.
So it doesn't really give you the linear. It doesn't talk about that. So are we gonna use that?
So we're not going to use
changing-
that. We also have this one. See?
Yeah, that's what I was gonna.
Yeah.
see.
If I use alpha, I have to find alpha. Although I can.
Okay. And then 3 seconds later, the angular velocity is 5 meters per second. So change in angle, which you can basically find out by using this, right? 3 seconds later. Wait, no, you can't. That's what it's asking for. Yeah. So average, what is it? Average angle velocity. Assuming it has constant acceleration, we could always just divide it by 2, right?
Well, this constant angular acceleration is actually the key. This is a requirement. In order to use it to be applied, I need to have this constant acceleration. Before
Yeah,
it's
that's what
constant
I was
acceleration.
assuming.
Yeah. Constant angular acceleration this time.
So just 3, right? That's 3.
Yeah.
And then T, okay. Displacement.
Yeah.
8. Oh, no, not 18. What's wrong with me? 9.
Yeah. 9 radian. Okay? Yeah.
Radian. Oh, yeah.
It's
Okay.
just yeah. For example, it's just that before we're talking about this kind of thing. Now, when you move it, when you rotate like this, you have to think about the angle, right? It's a little bit difficult to imagine, but you can think about it, right? Take a look at the central angle changing. So that's 6.
Yeah.
We can use
Okay.
the big 5. Angular big 5. 7.
Starting with zero initial angular velocity. Initial. Sphere begins to spin with constant acceleration, of course, about an axis through its center. Achieving angular velocity of this has displacement. Has acceleration. So it doesn't have time. We can no.
It doesn't really have the time. Sure.
Yeah, so that's what we're gonna use.
There's a formula without the time.
I'll just start off with the normal one. So V squared. Oh, yeah. All right, that works. Let me get rid of this.
Yeah, this one, right?
Let me. Yeah.
Yeah, you can totally use that V square thing and to basically kind of compare it by yourself. That's also a great way to do it.
Wait, sorry, I forgot. What is A again for this situation?
Oh, for this is alpha. It's the angular acceleration. Because
Okay, yeah.
before is the linear acceleration, now it's just angular. Whatever before saying linear something, now it's angular something.
Okay. So
So you might change it into alpha in case you confuse the view with A.
yes. Change that before it's too late. Okay. So it's saying we have a velocity 10 when it's at the end. So 100 equals 0 initial velocity, 0 plus 2, the thing we're trying to find, and then changing that times 20.
Yep.
Equals, turns into 100. 10 equals 4 at the unit artha. So 5/2 equals, and that would be meters per second. No. Radians per second.
Yeah. And it's angular acceleration, so second square. Right?
Yeah.
Oh yeah, you wrote second square. Yeah, that and then this is the comparison by putting it together. This is the definition of this. And because of the definition, we change all this into all this. We'd expand that actually.
Okay, so yeah, displacement equals the, okay, yeah, and then, yes, and then, wait, this one. Okay, yeah, that does make sense, because you did prove it, right, with the whole rotation around.
Yeah, arc length thing. Yeah, in geometry.
Mm-hmm.
So this is the big five, and eventually you'll find it's almost identical. It's almost very, well, they're very similar as the one that we used before.
Yeah.
The requirement is.
Since we have 5 minutes left, can we go back to the balancing where it's uniform density? Because I didn't really get it last lesson. Well, it wasn't very concrete.
Balancing, it's the previous chapter, right?
Yeah.
It's the very beginning with this, right?
Somewhere. I don't think it's the beginning.
Is it this formula?
Yes.
Well, you can just imagine that. Let's just use this one, because this. Think about seesaw. This gravity times this length is going to decide my effect of turning things, right?
Yeah.
So it's m2g times my x2, right? And plus, and this another kid is sitting here. And then it's m3g times my x3, right? Does that make sense? So this is x3. Oh, he wrote it here. Does it make sense? This is all the.
Yeah, I get this bottom part of this part though. The m1. So mass times. Oh, okay.
It's just a lot of them. You can imagine there's a 4, there's a 5, there's a 6, this kind of. It's so many of them.
Okay, so basically every single like dot that exists there, it's a mass times. It's how. Wait. Why would you want a mass if it's standard density?
I still want it because I'm using this to balance to basically simulate the way that we do seesaw, right? All the masses you have is going to have one big effect of turning this seesaw into this. This is a clockwise rotation, right?
Yes.
And then there's another big guy sitting here. And he's timing, well, he's imagine all the mass add together and times this is basically R center of the mass times the X equals to all the other sigma X times M. Does that make sense?
Okay. A bit. I could always just go back because I am planning to go back to like what was it where we started chapter 4 and then
Yeah.
this week just work all the way back because usually that's when I have the most difficulty in the class, like the beginning month.
Yeah, and also this is it's gonna help a little by rotations. I think that the next thing we learn it's talk about torque. Have you learned torque before? Basically, we talk about the seesaw again.
How fast it's rotating, kind of.
Yeah,
I
just
don't know.
you know how to, for example, this is a seesaw. Now it's balanced. It's not moving, right? Someone's sitting there, so it's rotate, right?
Oh yeah.
Start to
Mhm.
rotate. And if you don't want it, you use someone else to rotate in here, right? To sit in there. So this is a balancing of rotation. Does that make sense?
Yes.
And this is why we have this center of the mass formula. It's because one side is all the sigma m plus times the distance, saying x, since this one using x center of the mass, and balancing all the sigma m times x, which is m1 x1, m2 x2, m3 x3, this kind of thing. Does that make sense?
Yes.
Yeah, this is you can imagine the seesaw phenomenon, right? Does it make sense?
Kind of.
So what's left must balance it with what's right, right?
And then I might, once I get this down, I might look at torque.
Yeah. So this is basically about the torque. Why we are using this so sure about the seesaw is because now we know what's causing it, the one to rotate, is you have to give it a force. You also have to time a L perpendicular, which is this. Does that make sense? For example, you normally sit in a seesaw, you want to sit in here because this one is longer, right?
Yeah, so
Yeah.
are you saying that this L represents like how much leverage you get from the distance?
Yeah,
or is
kind
it
of.
just
Yes. It's
Okay.
actually, to be exact, and a lot of data accumulated, eventually we find it's the perpendicular distance from the pivot to your action line of the force. Which means if you do it in here, if you want to push it, you want to push it in here. You don't want to push it in here, right? Also, you don't want to push it in here because it has a less effect, right? Does that make sense?
Oh, so only the normal.
Yeah,
only
only
normal
the
sort of-
perpendicular distance from the pivot here, the one the point in the center, to the action line of the force. Perpendicular distance is this one. For example, if you do another one in here in this direction, then in this direction, you find the effect is less. And then if you do the calculation, you find it's working. What's working is in here. So that's why it's called perpendicular distance from the pivot to the action line of the force. Does that make sense?
Yeah.
Yeah. So you can see that sometimes there's a FR perpendicular or FR sometimes sine theta kind of thing. Does that make sense? It's using
Yeah.
trigonometry. So that's why we want to use this rotational effects. In order to balancing in a seesaw, you have to, there's a two requirement we see. One is all the mass have to be balanced, like all the, how do I put it? All the sigma F should be 0. And all the sigma F L perpendicular should be 0. Does that make sense?
Yeah.
Yeah. So that's why we have this equation basically. We didn't really use it here. It's a pity. but it's not far. So. In some textbook, they teach torque first, and then they teach center of the mass. Well, actually, it's in the history of physics too. We learn torque first, and then we learn center of the mass later. I believe so, yeah.
Yeah.
So that's why it's balanced in there eventually. Does it make sense a little?
Yeah.
Hmm.
Like without a perpendicular and.
Yeah.
I understand what this equation means. That's the good part. And then I'll tackle some of the questions by myself after this class.
Yeah. So all
hopefully
the
I'll be good on that.
Yeah. You can do all the exercise for this chapter 7 now. Briefly. And then all the questions that we did for chapter 9, actually that's 8, and then that's chapter 9, and then we stopped right before the torque. There's some extras that I can do too in the drill. Do you have other questions?
I think that's it.
I might answer the question about you have about this center of the mass thing.
Yeah, I understand what the equation means, and wait, let me look at the first question real quick. Sorry if I'm taking some more time.
Sure, it's okay. It's okay.
Oh man, what page is it again?
Let me see.
Oh, I see it now. Yeah, 2 objects, one with mass m, and then yeah, also what is it considering the center? Well, the mass of the bar, right?
Yeah.
So all you do is this. Wait, I have one last question.
Sure.
How do you do that for the bar itself, like the distance part? Do you use like a what is it, integral?
You mean how do I measure it?
Like yeah. I don't know why my thing.
I can use the meter stick.
Yeah, for like example 10.
Example.
It's saying
example 10. Oh.
Yeah, because the bar also has mass. So how would you measure like its total mass? This might be kind of a dumb question, but like the mass here. I mean, no, like not the mass, but the length, right? Because it's.
Oh, I can just pick any
different.
pivot. I can pick any pivot here. I can just pick this one as well, convenient for me. I can also pick
Yeah,
this
but what
one.
about like the mass here? What happens to that?
I also calculate it because this is a mass times this is 0, right? And this one is 3m times well, this is the center, and this is 3L over 2, right? For this one, I'm talking about all sigma mx, and this is the origin, and then this is 3. This is 2m, right? This 2m times 3L, right? So from here to here is 3L. Does that make sense?
Yeah.
This is all the sigma mx, and then equals to the peak, and then equals to all the total mass time my center.
Because especially for this part, right? Because there's so many things, you definitely need to take a sigma to like get all of them, all their mass.
Yeah. Oh, in this one I also consider it's just I use this entire thing. I do not use this entire thing. I use the center of the mass because this is a regular shape. The center of the mass is in the middle. So it's basically, I'm considered it's like kind of point mass in here. Does that mean? I'm not using that all this. Of course, because are you using the one that we learned today? Integration like
well, I'm trying.
Yeah. Using that is also okay. I'm using a point mass. It's just just for convenience, I guess. I can also use an integration. It's the same thing. The result is the same.
Yeah, like all these points here.
Yeah.
Including every single one. Okay, yeah, that makes sense. Well, I think that could be it for today.
Sure.
Yeah. Well, thank you.
Okay.
See you.
See you. And bye. Have a good week.
You too.